Hello guys, in this video we'll talk about your 9th lab. In this lab we will be implementing a part of very simple CPU. In this implementation we're going to only have 4 instructions. These are add, addi, bzj and bzji. Once we have completed this, we will be able to run assembly programs on your FPGAs. Before we get into designing this, we should remember the architecture of very simple CPU. In this figure, we can see the structure of very simple CPU. It has 2 main components, the core and the memory. The core is where the instructions are executed. This is represented by the file verysimplecpu.v in your lab. As for the memory contains your program and your data. This structure is represented by blram.v, which stands for block RAM. This means that you will be writing your program in this, as well as your data. And the contents of your memory are stored in the file data.v. In order for the core to communicate with the memory, we have the following communication ports. In order to select which address to write or read to, we have address to RAM signal. As you can see, this signal is a 14-bit signal. And then we have 2 data signals, one for data to RAM and the other data from RAM. Data to RAM is for writing into the memory. Data from RAM is the data you receive from your memory. As for our final port, write enable, this indicates that we want to write into our memory. In order to read a specific memory, let's say we want to read address 5, we would write 5 into address to RAM. We would disable write to enable, meaning that we would write 0 here. And then after 1 clock cycle, we would receive the contents of the address 5 from data from RAM. If we wanted to write something, let's say we want to write 15 into address 5, we would write 15 to data to RAM, and then write 5 into address to RAM, enable write enable, meaning that writing 1, and that's it. In the next clock cycle, the value 15 would be written into address 5. Next up, let's look at how our instructions are written in very simple CPU. So, as you remember, our instructions are a total of 32 bits, starting from the 0th bit up to 31st bit. And in these instructions, we have our opcode, our I bit, A and B. Our opcode indicates which instruction we are using. The I bit indicates the immediate mode. And A and B are the values to work with the instruction. As you can see, the opcode is 3 bits, the I is 1 bit, and A and B are 14 bits. Next, we will review the instructions we will use for this lab. First up, we have the add instruction. In this instruction, we take 2 arguments, A and B. We look into the value of A and B, add them up, and then write them back to A. So if we were to say, right, add 10, 15, we would look into the address 10, we would look into the address 15, add them up, and then write them into 10. So if 10 was 3 and 15 was 2, once we execute this, this would turn into 5. Next up, we have the immediate version of the add instruction. In this instruction, we use the value inside A and just the value of B. So if you were to do a similar example here, add I 10, 15, again is 3, 15 for this is not important. The value of 15 is not important. So let's say it's 2. So it is not going to add 3 and 2. It is going to add 3 and 15. And then we'll write it back to 10, meaning that 10 will be 18. Next, we have our BZJ instruction. BZJ stands for branch on 0. So what this does is, if the value inside B is 0, then our PC, our program counter, will be equaled to the value inside A. Otherwise, the program counter will increment by 1. Or if we can look at it from here, if B is equal to 0, go to the value of A, else go to next instruction. Then we have our BZJI instruction. This instruction is the jump instruction. You do not do any checks for B. Instead, what you do is you jump to the value here, which is the value of A plus B. So it is not the value of B, but just B, meaning that if it says B, say G, I, 5, 3, this would mean, well, let's say 5 has 2 in it. So this would mean, look into 5, it is 2, and then we have 3, so PC would be equal to 2 plus 3, which is 5. So now that we have reviewed the instructions, let's look at an example. This code is the code you'll be running in your simulation as well. So let's look at what's happening here. So first up, we have an add instruction, 10, 15. So in 10, we have 0, 15, we have 2. So if we add 2 and 0, we get 2 into 10. Then we have add I, meaning that look it into A, we have 2, and then add 20 to it. So now this is 22. And then we have a BZJ instruction. BZJ 3, 5. So we should look at the value of 5. It is 0. So if it is 0, we have to jump. We have to jump to the value inside 3, meaning that's 7. So from 2 to 7, we're going to jump here. Now we have another BZJ instruction. Here we're going to check the value inside 10. So the value inside 10 is 22, which is not equal to 0, meaning that we will not jump. So we will continue to the next instruction. And then our final instruction is a BZJI instruction. So what we'll do here is look into the value inside 9, 8, and then add the value here in the B. So we will add 0 to 8, which is 8. So it will jump to 8. This instruction will jump to itself, and we will end our program. Hello guys. In this part, we'll be taking a look at implementing our design. Here I have an empty project here in ISE. First thing I'm going to do is add my files. Here I've added the files I've downloaded into my project folder. I'm going to add these into my project. However, it is very important that you do not add data v. You have to put data v into the same directory as blram.v, but do not add this into your project. So I would recommend that you put all of these inside your project file and do not add data v into your project. So I'm going to add these. So here, as you can see, I have my files, and then here in your automatic includes, you will see data v. So let's take a look at our design. So first of all, we have our ports. In the last part, we've talked about these ports. You know clock and reset by now. Data from RAM for the incoming data from the RAM, the write enabled signal, address to RAM, data to RAM for writing to the RAM, and then P counter is your PC or your program counter. And here we have provided you with internal signals. You may, if you need to, add more internal signals, but you should be able to do them with all of these. Here we have our always at pause edge clock, and then at start block. Here we have written some of the code for you. We want you to fill in this part. So here we have implemented BZJI and the add instructions. So we want you to add the BZJ and add I instructions. So here, let's talk about what each state does real quickly. So this state will read the instruction from your RAM. So what does that mean? So if we were to say add 1015, the actual hex number that represents add 1015 will be read in this state. And then in the number 1 state, here you see that we have received data. So we entered the address here, and then we received it here. So as you can see, in the previous state, we said address is equal to P counter. So if your P counter was 0, you would write 0 into your address, and then in the next clock cycle, you would receive the instruction here. So here, the data from RAM right now is your instruction. What we're doing is partitioning it into correct components. So our opcode is represented by 31st to 28th bits. So if you remember, in the last part we had a figure showing all of these. So from 31st bit to 28th bit is your opcode. By the way, this opcode here includes your I bit as well. So that's why it is 4 bits, not 3 bits. Next, we have our operand 1. Operand 1 represents A. So this is from 27th bit to 14th bit. It is a 14-bit signal. You will write it into operand 1. And the same thing for B, operand 2, here from 13 to 0. And then what we do here is write this, which is operand 1, into the address. Why? Because in our instructions, in all of our instructions, we need to read A before doing anything else. And then we get into specific instructions. So here for BZJI, we went to state 5. For add, we went to state 2. And for BZJ and add I, you will do something here. So let's follow add here. Let's go into the second state. So in the second state, we will receive the value inside A and then write the address of B into the address port. So if you remember, here we wrote the address of A into the address variable. So now 1 clock cycle has passed and we're going to receive the value of A. So you can see that here. Number 1 next is equal to data from RAM. This data from RAM is the address we requested in the previous cycle. So our number 1 is set now, and for add we're going to need the number B, the value inside B. So what we're doing is writing operand 2 into address. And then since we don't want to write anything, we are disabling write enable. And you can keep data to RAM 0 since it's not going to write. So next up, we're going to the third state. In the third state, we're going to receive the value B. So the value of B will be inside data from RAM. So we're going to write that in none2. And then since we don't need to do anything else, we can do our calculation, which is addition, and write it back into the RAM. So for that, we do a check here. If our opcode is 0, which is add, if you want to do add, we use the number 1 we got in the second state and data from RAM to obtain our result, which we write into data to RAM. And then where are we going to write this? We are going to write this into the location of A. So we set the address to operand 1, which is A. Now it is very important to do the distinction between the operand and the number. The operand variable represents A, as in the instruction that you will see there. So if it says add 10, 15, my operand is 10, not the value inside 10. The value inside 10 is stored in number 1. And once we've done this, all of this, our add instruction is complete. So what we're going to do is we're going to increment the P counter by 1. So we're done with this add instruction and we're going to the next instruction now. So we have to increase our PC. Once we have done this, we can go back to state 0. So we have traced the add instruction. Now let's take a look at BZJI. So, as we've said before, we've come back to the 0 state, and then in 0 state, we read the instruction. And then if we encounter a BZJI instruction, let us see what happens. So first off, all of this part is going to be the same. You are going to read your instruction and then parse it. You're going to put the parts into the relevant variables. And then if your opcode is equal to this, it means you're doing a BZJI instruction. So you're going to go to the 5th state. So let's look at the 5th state. So if you remember, in BZJI, we do a single jump. We do not do a check. So we should be able to do this in a single state. So in the previous state, what we did was write the address of A into the address variable. So in this state, we received the value of A inside data from RAM. So what did we need to do in BZJI? We need to get the value of A and then add B into it and then jump to that location. So I have the value of A, and then the B value, not the value inside B, but just B, is stored in operand 2. So I add them up and then write this into pcount, our PC. And then rest of it is standard stuff. You keep write enabled 0, you don't write anything else, and then you turn back to state 0. And based on these, you're going to add BZJ and add I. So as we said, you're going to add these, and if you want, you can edit the existing states, for example, state 2. And then if you need it, you can write another state as well. So now that we've looked at the structure of your lab, I'm going to complete this assignment and then show you the simulation. Alright, now I've completed my assignment. Now let's go and simulate this. Once again, make sure that your automatic includes have data V here. So let's go into the simulation tab. Once you're here, you're going to want to press TV, highlight this TV, your test bench, and then double click Simulate Behavioral Model. Once you do this, your simulation should start. So now, here I have my simulation. In order to see it better, I'm going to change all of these into unsigned decimal. So the code we're going to trace is here. So I'm going to put this next to our simulation. Now, let's look at our code. The first thing we do is an add instruction. So what we're doing is add 10, 15. So what we first need to do is read this instruction. So by default, when the module starts, the program counter starts at 0. You can see the program counter here. So as you can see, it starts with 0. So let's go to the time where reset has ended and we have started our program. So the reset signal has ended here. So we're going to start processing here in the first positive edge. So in the first clock cycle, we're going to read our address, rather our instruction in the 0th address. So as you can see, the address to RAM is right now 0. So in the next clock cycle, we will have this in our data. Here in our data from RAM, you can see this number. This number might not make a lot of sense right now. That is because it is our instruction word. If we were to separate it into components, you will see that it would represent this. So once we have this instruction, what should we do? The first thing we should do is read the value inside A, which is 10 right now. So as you can see, 10 was written into the address. And then once we have that, which as you can see from the data, it has returned 0. Here, let's look at 10. The value of 10 is 0. So once we have the value of A, we have to read the value of B, so 15. So let's look. We wrote 15 into the address. So in the next clock cycle, we should get the value of 15. So let's look at the data from RAM. Here we see 2, which is the value of 15. So once we have these, what do? We get 0 and 2, the values we've found, we add them, and then we write them back into the 10th address. So our address is set to 10 again. Our data is set to 2, and write enable is enabled. Once we do this, the value 2 will be written into the 10th address. So next up, we have this instruction. So here it says 1 in the address. Why is that? Because we want to read the first address where our next instruction is stored. And before I forget to mention, you can see that the program counter has incremented here. So that is actually what we're writing into the address. So once we do that, we're going to receive the instruction in the next clock cycle. So let's look at data from RAM. Here we have received the instruction. So we've determined that it is an add I instruction. So what we're going to do is first we're going to read the value of A, which is again 10. So we write 10 into the address. Once we do that, we're going to receive data from RAM. Once we do that, we're going to receive the value of 10 in the next clock cycle right here, which is 2. Right, so now we have the value of 10, which is 2, and then we're going to add 20 into it. Not the value of 20, but just 20. So what we do is add 2 to 20, which is 22. We write that data to RAM, enable, write enable, and once that's done, in the next clock cycle, that will be written into our memory. So this is done now. So what we're going to do now is go to our next instruction. So in order to read our next instruction, we're going to write the address that we're going to write the PC into our address. So our PC now has become 2, and we write that value into our address. So we wrote 2. So in the next clock cycle, we're going to receive the instruction that is BZJ35. So that instruction is right here. So once we read that instruction, what we're going to do is we're going to get the value of A once again. So we write 3, which is A, into our address. And then in the next clock cycle, we will receive the value of A, which is 7. So what else do we need to do? We need to get the value of 5 and see if that is equal to 0. So we write 5 into the address, and then we receive a 0. So since 0 is equal to 0, we're going to jump now. Where are we going to jump? We are going to jump into the value of A. So as you can see, the value of A was what? The value of A, which is 3, is equal to 7. So our program counter should be equal to 7 now. As you can see, the program counter went from 2 to 7. So now we're in the 7th instruction. So to read the 7th instruction, we're going to write that into our address. And then here, you can see that we've read our instruction right here. And then what is that instruction? It is another BZJ instruction. So once again, what are we going to do? We're going to read the value of A, which is 3. We write 3 into the address. We receive the value 7. And then we're going to read the value of B, 10. We write 10 into our address. What do we receive? Receive 22. Now, we need to check the value of B, if the value of B is equal to 0. So the value of B is 22, and it is not equal to 0. That means that we are not going to jump, but instead we're going to go to the next instruction. So our program counter is going to increment by 1. So here you can see that our program counter is 7. We're going to increase it by 1, and then which is 8. And once we come to the 8th instruction, what we do is look into the value inside 9, which is 8, and add 0 to it, which is again 8. So it's going to jump it into itself. As you can see here, the program counter doesn't change and the program ends here. So that concludes our simulation. If you have done this correctly, you should see total errors is equal to 0 and simulation successfully completed. If you have errors, we're going to receive error messages about it, telling you the time and which instruction you've done incorrectly. And then it's going to say your simulation has failed. So if you receive these 2 comments on your log in your console, your assignment has been completed.
Hello everyone, and welcome to CS240's Lab9 video. And so far in the previous part, Buğra talked about part 1 and part 2, and in this lab we're working on a very simple CPU design. You're basically designing your very simple CPU cores. In the initial initial file, we have already given you these operations that are implemented, and let me actually go over to them and show you. This would be the file that you will be working on, and as you can see here, our BZJI and add instructions are implemented in here, and as you can see, this would be BZJI, and this one is add instruction, and you can see the ID of the instruction, and you can check it is the correct ID. Maybe I should say opcode instead of ID. As you can see here in the instruction set JPEG file, you can see that add is 0, NAND is 1, SRL is 2, and these are just the 3-bit of the opcodes basically, and we have our immediate flag here as well. So if we are working on just add, it's going to be 0, 0, 0 and 0. If it's add I, it should be 0, 0, 0, 1 basically. And you will have to code your design according to that. Okay, in this lab, we want you guys to, at least in part 2, we want you guys to add these instructions into the CPU core, into the design, and test your code using the versatile CPU test bench that we should have in Lab9 part 2 folder, this file. And you need to run the simulation, and actually we have already shown you, Buğra has shown you how to run the simulation on Xilinx and how to go through it in the previous part of this video, so you can see that one. We have already also given you the memory data of this assembly code, and let me show you the assembly code actually, and also the data. As you can see here, this data here corresponds to these instructions, and these data are basically corresponding to these data as well. So you can just use these files to run your code in the test bench, and you need to check if the test bench is successful or not. And if it is not, you should make it correct, make the CPU core correct. And let me see. Okay, as you can see here, you just need to add these files, and also remember to put this data.v file in your Xilinx project folder. For example, like let me see if I actually have it in Lab8. I might have it. Okay, I do not. Maybe I have it in project CPU that I have created already. Okay, my Xilinx project is in this folder for project CPU, and as you can see, all the files are here, and you need to put your data.v in this folder, in your very simple CPU design folder, basically. That's what you need to do. So let me go back to Lab9. And after you're done with implementing BZJ and add, you will have done 4 instructions, 4 operations. So you can move on to part 3. And in this part, we want you guys to implement CP and CP little I, CP immediate. And you know what these instructions are. These are also in the example code here. You can run them on verysimplecpu.org to see if your test batch is doing the same as verysimplecpu.org does. And again, in this part 3 folder right here, the data file is given to you already. So you just need to update these in your Xilinx project. Actually, it would be better if you had 2 separate projects for these parts, so you don't lose your files. I would suggest you doing that. And what you need to do is just implement, basically, let me scroll down. Just implement these 2 instructions, and then these 2 instructions, and you're done. You just need to submit this file, the verysimplecpu.v file, just that, and you don't even need to zip your file or anything, just upload it directly on LMS. And also, just as a reminder, your project files have been given on LMS. You need to be doing these projects the due date should be, let me actually check the due date. It's 3rd of June, so you need to complete them approximately in 2 weeks. So just download these files here and then start your project. You just need to design a simple CPU, which we have given the starting file here. You can just modify this file and then finish your project, and we will probably be talking about them in the lab as well. So just keep those in mind and attend the labs basically. And if you have any other questions on the labs and CPU, the project CPU, you can just email us and I guess see you in the next labs.